holding hands. Right, so if we're drawing out a circuit and we've got some resistors in series, and the fifth cycle limits us to 3 resistors in series. But well, our equations will work no matter how many we had in series. All right, so what's this here? What have I drawn? A battery. Which side has the positive terminal?
Left.
The left. So our negative terminal is the right. In which direction does the current flow? Anti-clockwise. Which direction are the electrons actually moving? Clockwise. So current is not an actual thing, or we don't have our positive charges moving, but we still calculate current as being movement of positive charge. So these are my resistors. And I'll call this one R1, R2, and R3. And it doesn't really matter what they are. At the moment, the rule for resistors in series is current is constant. Now the reason why the current is constant is there's only one pathway. So the electrons are all going to have to travel at the same rate through the circuit, and they have to go through the same wires and the same resistors, so our current is constant. If we have V equals IR as our pretty standard equation that we use a lot for these kinds of questions, then the voltage is determined here by our battery. Okay, so that we know that one. And the current is constant for the whole circuit. So this is the question then, what's the story with our resistance? And our resistance is going to now be the total resistance for the circuit. And the total resistance when we're in series is just equal to the sum of the resistors that are present. Okay, we just add them together. So we can still calculate, an unknown in the circuit with resistors in series. Oftentimes you might know the resistance of 2 of them, for example, and you might need to find the resistance of the third, kind of thing. Or you might be given the resistors and you have to find the current, all different kinds of variations of what that might look like. Let's work through what example 6.7.1 on page 40. In this case, it tells us that we have a 20 ohm, 30 ohm, and a 50 ohm resistor connected in series in a circuit to a 15-volt power pack. We're asked to find the total resistance as part A. So RT will equal 20 plus 30 plus 50. are 100 ohms. The current flowing in the circuit, well, if V equals IR, I is equal to V on R, isn't it? We have to divide both sides by R, but this has to be the total resistance of the circuit. And so I will equal 15 divided by 100, 0.15 amps. And then part C, the voltage drop across each resistor. And so you might remember from that little animation I played you that when we have our resistors in series and they were light bulbs, it was like a step down each time. Each time we went through a resistor, our little red bulbs got lower until they got to the bottom, where they were at the same potential as the terminal that they were heading back towards. So it's this. That's why we calculate the voltage across each resistor. Okay, so see here, the voltage then across R3 will equal the current times the resistance of the third resistor. So it will equal 0.15 times 50, which is 7.5 volts. The voltage for resistor 2 is the same current multiplied by the resistance of that resistor, 4.5 volts, and the voltage for resistor 1 is 20, it's going to be 3 volts. Now, a way to double check that you have calculated correctly is that when you add these up, they have to add up to the total voltage that we have in our system. Okay, so you can double check that you've calculated those potential different drops correctly by comparing the total with the total voltage of the system. Okay, now we have worked example number 2. Let's have a look at it. A 25 ohm resistor is connected in series with an unknown resistor. This one's 25 ohms. This is an unknown. The current flowing in this circuit is 0.50 amps. The voltage is 24 volts. And we want to know then what's the resistance of this resistor here. Now, if V equals IR, and this is the total resistance then, we can rearrange this to see that the total resistance is equal to the voltage divided by the current. So if we substitute in our voltage, 24 divided by 0.5 is going to give us 48 ohms for our total resistance. So if RT is equal to R1 plus R2, 48 is equal to 25 plus R2, our unknown. So therefore R2 is equal to 48 subtract 25. either find an unknown resistor or find the current. They're the most common. Or you could also be finding the voltage. Alright? So because the current is constant for our resistors in series. Now we're going to look at resistors in parallel. And resistors in parallel look like this. Our electrons moving through our wires, now when they come to these junctions here, there's multiple pathways they can take. There's not just one anymore. So if it was electrons that are traveling and our electrons will be going in this direction, as they come to this junction here, they can go that way or that way, can't they? And this changes things. We don't have that constant current anymore. So this was electrons. But if we've got multiple pathways for our electrons, you can see that the current's not going to be constant. But the voltage is. Okay? So because we remember that if in our that little animation that if we lift up our potential on to the same potential as the battery, if we're wired up parallel to the battery. Okay, and so the voltage, if this is 24 volts across here, if I put a voltmeter across here, it will also measure 24 volts. And a voltmeter across here would also measure 24 volts. Because they're at the same potential as the power source. Now, for our resistance though, in a parallel circuit, we have a different formula for the total resistance. It's the resistance, and we only ever do two in parallel. So that's why we use it in this format. R1 times R2 divided by R1 plus R2. Now our voltage is constant, but just like we could add up our resistors in our circuit with our resistors in series, we can add up our current. This is actually Kirchhoff's law, that you can add up the currents. Now you might notice that when I've put my voltmeter onto my circuit here, I have put it in what we would say it's in parallel as well. It's not in series, okay? Because if it were in series, the electrons would have to go through it. But the electrons don't have to go through it, and we don't want them to go through it because voltmeters have very high internal resistance. Because they have very high internal resistance, that means the electrons don't want to, or they don't go through the voltmeter, and the voltmeter can then measure the potential difference across where it's connected to the circuit, because none of the electrons are leaking through it. whereas our ammeter very low internal resistance. And so it goes in series. If I would put in an ammeter, it goes into the part of the circuit where I want to measure the current. Because the ammeter has very low internal resistance, it's not going to slow the electrons down while they're going through it, and it will give us an accurate reading of how fast they're going. Okay? Remembering here that current is the movement of positive charge, and what I've drawn though is the movement of electrons. Okay, so our worked example, we've got two resistors, one of them's 30 ohms, this one's 50 ohms, and they're connected in parallel in a circuit to a 15-volt power pack. Determine the total resistance of the circuit. That's our first job. So A, RT, R1, R2, divided by R1 plus R2. So that's 30 times 50, divided by 30 plus 50. 18.75 ohms. This is the total resistance of the circuit, even though this is 30 ohms and this is 50 ohms. The total resistance of the circuit is much lower than each of the individuals because it's wired in parallel, and we've got these options for our electrons to flow through. Second part B is the current. Now we want to firstly find the current through the 30 ohm resistor. So R is equal to 30 ohms. Remembering that the voltage is constant, so 15 volts for all of our resistors in this circuit. So I will equal V on R, which is 15 divided by 30, 0.50 amps. And then the current through the 50 ohm resistor. Okay, remember that our voltage is constant. Also notice that if the current is the measure of how fast the electrons are flowing through the resistors, it makes sense that they can go faster through the lower resistor. So it's faster through the 30 ohm and slower through the 50 ohm because there's more resistance, they have to go slower. And then the total current is just going to then be, so C, IT is equal to I1 plus I2. So it's just going to be 0.50 plus 0.30, 0.80 amps for our total current. Got another worked example on page 42, so let's have a look at it. Any questions or comments so far, or is it okay?
So that little, so the current total, that little formula that you've got there, is that the only one that's not on here? It's just something we have to remember, is it?
So it's not on there?
No, it doesn't look like it.
I don't think the voltage or the resistances, like you haven't got a VT equals V1, V2, basically what you've got are how to calculate a resistor value for circuits in series and parallel. And then you have to know those facts about, I guess, the current is constant for series and voltage is constant for parallel. Yeah, you have to memorize that if you like. All right, so we're done. It's always a good idea to draw yourself a diagram so that you can see what's going on. If one isn't provided for you. So we have a resistor of 40 ohms in parallel with a resistor of 70 ohms, and a current of 0.50 amps flows through the 40 ohm resistor. So if I put in an ammeter here, and it's measuring 0.50 amps, determine the voltage across each resistor. Now, we know our current and we know our resistance here. So V equals IR. And so our current is 0.50 and our resistance is 40. Gives us 20 volts. Now, that's the voltage across this resistor, but voltage is constant, so it's the same voltage for the 70 ohm resistor. Okay? So now we know this is 20 volts. And determine the current flowing through the 70 ohm resistor. And hence the total current flowing through the circuit. Now we've got I for our 70 ohm then is equal to V on R. If we just rearrange our formula here, we know that the voltage is constant. So it's 20 divided by 70, which gives us 0.29 amps. And then it was to still part B where we want the total current. Going to be 0.50 plus 0.29, which is 0.79 amps. And if we double check, we see that a higher current is still going through the resistance or resistance, 0.5 here, 0.29 there. That makes sense. So we can just double check. All right. We have some questions that we can